live again. Alright, let's see, what are we going to do today? I want to talk about ODP 410. I want to talk about passing strings to functions. So we started playing with functions yesterday, so I want to look at the ODP we just did and talk a little more about functions. And in that pick function we were passing and receiving an integer. What I want to move to today is how we do a similar thing but for passing strings. And strings, remember, in C are basically an array of characters. And so once we can pass a string, we'll be able to pass arrays more generally, arrays of integers or whatever we happen to have. So we'll talk about that, and then I want to talk about functions with respect to PA2, your stick program, and kick around some ideas on how we can use functions to make our program easier to write and debug and work with. And then we're working towards this whole business of char star star argv and trying to understand arrays of strings, char star stars, and two-dimensional arrays. So that's kind of our game plan for the next couple of days. So let's go ahead and do an attendance ping in the beginning here. Let me know you're here. And let's take a look at ODP 410. So the ODP we just did, you're writing a pick function, takes an integer, returns an integer. So one thing to keep in mind with functions in general, unless the description of the function is that it should print something, your function should never print things. Right? For example, the square root function does not print anything. If I call square root of x, right, I would be really startled if that square root function decided to print the value of that square root. Instead of printing, it returns that value, and then whoever called it can choose if they want to print that value, or they want to do something, or they want to print it with some stuff in the beginning, or whatever. But generally, functions should do what they're supposed to do and nothing more. And so the pick function was exactly like that. It takes an integer, if we call it n, it calculates one of two quantities, n mod 4 or a 1 if n mod 4 is 0. And then it just returns it. And so, in your stick program, you're going to want to do this calculation, but you're not necessarily going to want to print that number the same way that somebody might make their pick function print it. So you just want to call this, get back that number, and then you can print something like the computer is taking 3 sticks or whatever, and then you can use that number and subtract it from your stick pile size and whatever else you choose to do. So a pick function that would work for that assignment would be something like this, right? So take an integer n, and you didn't have to do this, but I just calculated n mod 4 and I saved that in an integer r, and then I said if r is 0, let's return 1, because that's the special case, right? Otherwise, we just want to return n mod 4, which is n, so we'll just return r. And you could say if n% 4 equals 0, return 1, otherwise return n% 4. It does exactly the same thing. And in fact, a good compiler, if you did n% 4 here and you did n% 4 here, it would actually do something like this for you. It would calculate it once, save the value, and then just use that value here and here. And you can do an if-else, right? There's nothing wrong with that. You could, I saw a number of people who did, if r equals 1 or 2 or 3, then return r, otherwise return a 1. That works fine. Or, if r is bigger than 0, then return r. I mean, there's a lot of ways you can write this. And I've said this before, I'll keep saying it. I want you to find a way that makes sense to you, right? in terms of the logic of your code, in terms of what do I do first, what do I do next, what conditions should I check. I want that to be what feels good to you, right? Because that's the whole essence of programming is how do I devise an algorithm? What steps should I ask the computer to perform to do some task? That's a creative process, right? You could make a checklist and say, if you're going to do this, do this. If you're going to do that, right? But let that come from yourself. And you know, if you do this with 3 if statements, there's nothing wrong with that. If you do it with 6 if statements, there's nothing wrong with that. We can work later towards, you know, I must write this with only 5 lines of C code, right? How do I restructure this? Or I want this to run, you know, a nanosecond faster. How do I change things around, right? But that's not the heart of programming, right? So do what's making sense to you. But that's one version of that is that pick program. So let's look at passing arguments to functions, and let's expand it to strings. So, you know, in the case of pick, our program looks something like that. And in our main program, whether it's your test program, I saw lots of people writing test programs. That's so awesome. It's been pretty hard traditionally to get people to do that, so thank you for writing those. So whether it's your test program or, you know, the test bed for the assessment, in here, you know, we could say something like, you know, integer r equals pick, you know, some other integer variable. Doesn't really matter what expression this is, but this expression is evaluated at runtime until you've got an integer, just a plain old number. And then this code is executed, but in the beginning, this variable n is set equal to whatever that number is that you passed. So this is passed by value. And you'll hear lots of people talk about pass by value and pass by reference and all this, but all we're saying is, you know, when you call a function, we actually calculate the in this case it's an integer, the numeric value of this expression, and then when we start running this code, we set this variable equal to that numeric value. So it's not like this is using the variable input, it's using the value of the variable input. And that's important. In particular, if somewhere in here I said, you know, n equals 7, that has no effect on input. That doesn't change the value of this variable in the main program. Because all I passed was the value of input, I just passed a number. And n got set equal to that, well here I'm changing n to be 7. But that doesn't go back and change this. All right, so and then the return we talked about yesterday, right? When I say return whatever, you know, tilde, right? Basically all of this is replaced by whatever expression we returned. Alright, and so whatever this returns, this expression here would say, you know, integer r equals that. If your main program did something like, you know, printf %d pick something, right? Same thing, this value gets loaded into n, the code executes whatever it returns, that becomes the value of this, and so now it becomes printf quote %d unquote comma some integer. What integer? Well, whichever one this function returned. All right. So that's basic functions. Integers are the easiest types of arguments to deal with. If you're getting a program when you're trying to compile saying implicit declaration of function, remember in our main program we need to tell main what type of function pick is, right? We're using this function pick, but it doesn't know about it. It's not defined in standard I/O. So before we start our main program, we would need to do a prototype, integer pick, parentheses, integer, and then a semicolon at the end. And the semicolon is super critical. If we just say integer pick something and we start a curly bracket, that's what we call the function definition. That's where we're actually defining what the function does. But when we do this, that's a function prototype. And we're saying, hey, I'm not going to tell you, how pick works. I'm going to tell you what it looks like. Something we sometimes call the signature. It takes an integer, it returns an integer. And then when it gets down here, it says, oh yeah, pick, I remember that, what was that? It takes an integer and returns an integer. Okay, that's cool, that's an int, we're good to go. And it won't give you that warning message about implicit declaration. Alright, and yeah, if you're coming to class a few minutes late, just shoot me an attendance ping when you get here, and you're good. Stuff happens. I'm late sometimes. All right. So let's see. So that's passing integers, right? It gets more interesting when you want to pass an array. And so let's talk for a few minutes about arrays, and then we'll talk about strings, which are really just arrays of characters. So arrays in C. And so integer arrays are a pretty typical thing to pick on. Hey, I can move my camera. I can say integer x bracket 10. And bingo, I'm done. There's an array of integers. And once you declare an array like this, what can you do? You can, in your code, talk about things like x bracket 0 or x bracket 2, all the way up to and including x bracket 9. And I basically have 10 new variables. And they all look similar to x, but each of these 10 variables is accessed by saying x bracket some number, right? This number is called the index. And so x bracket 0, x bracket 1, all the way through x bracket 9. Those are 10 variables that are part of this array. And most languages have a way to implement arrays. In C, right, we declare our array by just saying x bracket 10. The nice thing about arrays is that, if I was an integer, we could say x bracket I. And at this point, if the value of I was 0, this refers to x bracket 0. If at this point the value of I was 2, this refers to x bracket 2. If at this point the value of I was 500, x bracket I would refer to x bracket 500, which is not part of this array. It's probably going to hit an area of memory we don't have access to, and we'll get a seg fault. And this is where we get most of our seg faults, directly or indirectly, is from using arrays and messing up with the index value. All right, now C does something really kind of funny with arrays. This makes really good sense from an assembly language point of view, but it tends to drive programmers crazy particularly if C is the first language they're learning, because it just feels really kind of weird. So when I say x bracket 10, what I'm actually doing is two things. So integer x bracket 10. Does two things. One, it says find a spot in memory for 10 consecutive ints. And if this is the first time you've heard me talk about memory with respect to C programming, get used to it, okay? We've got to start thinking while we're writing code about what's going on inside the computer, the CPU memory system. The more we can sort of be having this mental image of what's actually happening at the hardware level as we write software, the more some of this stuff is going to make sense. And if you're like what I was like in school, where I was like a pure software person, didn't want to have anything to do with hardware, you know, that's challenging. But as soon as you can start doing that, things get easier, right? So when we say integer x bracket 10, there's, you know, our CPU, and there's a memory, and they're connected to each other. And we may as well mention, you know, there's an I/O subsystem. But that's basically your von Neumann architecture, right? So what is your memory? Your memory is, well, we could think of it as a bunch of flip-flops from Engineering 250. So a bunch of things that store bits. No, they're not actually flip-flops. They're little capacitors that store a charge. But we can think of them as just things that store bits. And if you take, you know, a bunch of these and put them out side by side, you can store collections of bits like bytes. So in some way, we have all of this storage available in our hardware, and we have ways to address each of these locations. So this might be location 0, 1, 2, 3, 4, 5, 6, 7, and so on, up to, I don't know, on my laptop I think it's 16 billion, because I have 16 gigabytes of physical memory. But it's basically like, well, it's kind of like an array, right? All right, so when I declare integer x bracket 10, first thing it does is it says, hey, let me find 10 consecutive memory locations where I can store integers. And let's suppose that, you know, it's going to start off right here at location 5, and it's going to store x bracket 0, x bracket 1, x bracket 2, and so on, down to x bracket 9. So there's the 10 locations in memory where it's going to store my array. So it finds a spot for that, and it does some magic to reserve this space so that somewhere else, something else doesn't say, hey, I'm going to store, you know, the variable j right here, right? So it marks that as being in use. So that's one thing it does. The second thing it does is it sets x equal to the address of the first integer in the array. So assuming that the compiler and the linker decided, you know, that my array is going to go here starting at location 5, it's going to set x equal to 5. Alright, this is like an entire course in computer architecture shrunk down to one page, one aspect of computer architecture. When you make an array in C, two things happen. The system allocates space for the elements in your array. If I say, you know, integer x bracket 100, it will find space for 100 integers. If I say character temp bracket 120, it'll find space in memory for 120 consecutive characters. And then whatever variable name I used here, it sets that equal to the address where the first element of the array is. All right, questions about that? Because if you believe this, then the rest of this gets easier. But if you don't believe this, or it doesn't make sense, then it's going to get more and more confusing. And if you're not sure, then come back and check this later. Alright, so those two things happen. We allocate space, we know that, but the real kicker is x is set equal to the address where that array begins in memory. And side note, right, integers, you can't store them in consecutive locations. Integers take 4 bytes. So, if this first integer was stored at location 5, it would actually be in locations 5, 6, 7, and 8. And the next element would be in locations 9, 10, 11, 12, and so on. But I'm just kind of doing a sketch here. All right, so X is the address of something in memory. And in C, when you have an address, we call that a pointer. So pointers are just addresses in memory. And so if we say something like integer star X, that's a really horrible looking asterisk. Integer star X. This is another way we can tell the compiler, hey, X is pointing to a memory location. In particular, a memory location where we expect to find an integer. And so the kind of secret about arrays in C is that whether I declare integer x bracket 10 or integer star x, x ends up being the same kind of thing. It ends up being a pointer. And so you'll hear people describe arrays as being pointers. This is why, right? Your array is actually your variable that you declare to be an array is just, referring to some location in memory. But there's a difference. If I say integer star x, what does the compiler do? It only does one thing. It basically makes a note to itself that x should point to an integer in the memory. Right? Integer star x says, hey, compiler, remember, x should point to an address in memory where there's an integer. It should, but it actually doesn't. Not yet. And so this is another thing to keep in mind. C does not generally initialize stuff. So for example, if I say character C, what am I telling the compiler? Hey, C is going to be a variable that holds a character. Right? C should hold a character, but it doesn't yet. If I try to print C, I have no idea what I'm going to get. I'm going to get something random. I'm going to get whatever happens to be in the memory location that the compiler set up for C to use. Right, now if I say C equals, quote, H, and then I try to print C, it's going to print the character H. So same thing here. This is saying what kind of variable X is, but it's not actually giving X a value. So if I went after this and I said something like X equals 5, and don't do this, we don't usually set pointers to numbers, but if I were to do this, say X equals 5, then what would X be representing? It would be a pointer to this location in memory, which, if the compiler had set up an array of 10 integers starting at location 5, well, X now refers to this first element of the array. And we don't usually just say X equals 5, but, before we can use X, somewhere X has to get a value. Right? If we just say integer star X and we try to do something with X, we will get a seg fault. So let's start generating some seg faults. So we'll do seg fault 1. Yeah, I'll keep it simple. All right, so declare x to be an integer, and let's just go ahead and print out the value of x. All right, so if I run this code, I get a 0. I'm printing out the value of x. I didn't give x a value. If I come back and I run this later, I might not get a 0. I might get some weird big negative number around 2 billion. Right? X is uninitialized. But I happen to be getting a 0. All right, if I say integer star x, and I run this, why am I getting a 0? That's not what I expected. All right, I'm getting a 0. That's fine. All right. So I'm making x a pointer, and I've asserted that a pointer is the same thing as an array, right? So if I say integer star x, it's basically saying x should point to an integer in memory. It should point to something like, you know, the beginning of an array. So if I try to do something like this, like print x bracket 0, right? There's my good old segfault. And the problem is that, you know, x hasn't been made to actually point to an integer yet. I've said x is going to point to an integer, but it's not actually pointing to an int yet. So I could do something like this. I could make an integer j equal to 123. And I could say x equals ampersand j, which means it's given the value which is the location in memory where j is stored. And so let's see what this does. All right, so I've set j is an integer equal to 123. I've said x is a pointer to an integer, and then I said x equals ampersand j, so the address of j in memory. So ampersand var means the address where var is stored. So I said x equal to the address where j is stored in memory, and then I'm going to print x bracket 0. All right, so here's our memory map. We're going to draw a lot of memory maps. We'll draw more of these in CSE222, but we'll do a good number of these in this course too. So somewhere is a location where my variable j is going to be stored. Let's say j is stored at location 20. When I say j equals 123, what does the compiler do? It says, okay, where's j stored? Location 20. Okay, let's store the number 123 in there. So it's going to write a 123 into this location in memory. And then it says x is a pointer to an integer. So x gets stored somewhere. So maybe up here at location 10, it stores the value for x. But at this point, x doesn't have a particular value stored in there. So we tried printing it out. It turned out to be a 0, but that was just kind of random luck. There we go. All right, but then here we say x equals ampersand j. So what does the code do at this point? Ampersand j says, let's find the address where j is stored. What's the address where j is stored? It's a 20. Let's set x equal to that. So that's going to put a 20 right here. And then if I print x bracket 0, right, remember our picture here, x bracket 0 is the thing at the location in memory corresponding to the value of x. Well, since x is equal to 20, x bracket 0 would be the thing stored right here. And so it should just print out the value of j. Oh, that was weird. So if we run that, there's x bracket 0. Now what is going to print if I print out x bracket 1?
You get a seg fault?
I might get a seg fault. If I don't, it would print whatever happens to be in this next block of memory. Whatever's inside here, which I haven't given a value to. So really got no idea what it's going to print. And if this happens to be an inaccessible location, it will definitely seg fault. But we might luck out, and there might be something in there that we can print. In which case we'll see that. So let's try that. Alright, so there's our weird number close to 2 billion. And if I run it again, I get a different number. This is uninitialized memory. Right? So C does not generally initialize stuff. So this is, you know, just whatever happens to be in there. And if I try to go, you know, too far away, well, I didn't seg fault, so I lucked out. So you know, there's stuff in there.
So it's completely up to how the computer allocated you memory. If you do or do not get a seg fault, you can try to index that far.
Mm-hmm. Yep.
Okay. What if you tried to make x point to a char?
Oh, that would be interesting. So let me try my negative index first, because I'm feeling like maybe I can get a seg fault like that. Probably not. Yeah, so that's valid. So what's happening when I'm printing x bracket minus 1? It's just doing the math, and it's printing, you know, whatever happens to be stored in memory right before my variable j. And if I do something like this, so let me just find some other integers there. Right. Well, x bracket 1 ended up being equal to 42. What was that? Well, that was the variable that I declared before my variable j. So we could start to understand a little bit about how the compiler is actually generating the machine code to execute our program, right? It's apparently storing this variable right after this variable in such a way that when I try to look at the location after j, I get to my variable jj. So yeah, what if we made this a pointer to a character? And I will almost certainly get compile warnings, but probably not a whole lot of badness when I run. So x0 ended up being 123. x1 and x minus 1 changed. But in some sense, a pointer is a pointer. But if I tried to make j really big, let's see what it does. Right, so it looked like it truncated it. I got x bracket 0 equals minus 68, which is not the value of j. So we can play all kinds of games, we can get into all kinds of trouble, but we can also learn a lot about how these things are set up and used by the compiler. And this is the other thing, right? You know, C or any other high-level programming language is there to kind of like make it easier for us to program. But still, if we can think in terms of what the assembly language is going to look like, that's going to make us more successful, especially in C, and especially when we start dealing with pointers and memory addresses and things like that. It's going to help us if we can keep kind of in our minds coming back to this idea of the assembly language version of our code and seeing what the compiler is trying to do.
Another cool thing you could do is like print out a struct in a binary file and then read it back in.
Yeah.
Just read it perfectly fine.
Yep, definitely.
You don't parse anything.
Yeah, cool. And so just for kicks, let me put this back to an integer, and let me print out what the value of x is. And this will give me more warnings. But x is this weird looking number. But x is a memory address. And so printing out a memory address as an integer, we don't usually do. We usually want to print memory addresses in hexadecimal because they'll be more meaningful. And we don't know necessarily if this is a 32-bit address or a 64-bit address. It depends on the architecture of the machine. So printf will take a %p that says I want to print something that is a pointer, and it'll format it nicely for us, and it'll avoid the warning. And if we print out the value of x, it's this number, and we're going to see numbers like this a lot. 0x7fff d61a 632d4. So this is a 64-bit memory address. And this is the location in memory where this variable j was stored. Right? We said x equal to the address of j, and that's telling us where j got stored. And it's different from run to run. But it's generally, you know, 0x7ff something. All right, so let's get down to nuts and bolts, and let's look at ODP 411B, and see how we can use all of this to get 10 out of 10. So 411B, you're writing a function named parse, and parse is supposed to accept a char star and then return an integer. And your char star is what? It's a pointer to a character, but it's also an array of characters, which is also in C a string. So this is like, you know, temp bracket 120, something like that. And once you have that array of characters, you do your usual scanf stuff that you've done before, right? Do an scanf, for %d followed by a %s to pick up extra stuff, right? And make sure that this returns, that your scanf returns exactly 1, right? So you've done this before. We did it with command line arguments. This time we're doing it with a string which is passed to a function. So let's look at passing strings. Alright, so here's one way to load a value into a string or a character array, right? This is an array of characters. I ask you to say something and I'll call fgets. So that's one way to read a value. And then let's pass this to a function. So let's say, you know, integer r equals parse, and we'll pass that. And I'll just print out r and we'll be done. Alright, I'm going to put my parse function right in here so I don't have to keep switching back and forth between two windows. So let me prototype my function. And I'm going to prototype it as returning an int but taking a char star. Now why am I taking a char star? Because my parse function doesn't know if I declared this array to be 120 characters or 1,000 characters or 5 characters. And if I said char bracket 120, this would only work if my array happened to be 120 characters. But it will always work if I say my argument is a char star. So I'm going to do the following. So I'm just going to say char star string. String is going to be the name of my argument. And I don't know, let's just do the let's just do something sloppy. Let's do an scanf of string and %d and value. And I'm just going to return the value. All right, this is not ODP 411B. I'm not looking for extra stuff. I'm not making sure that my scanf returned a 1, meaning that it parsed an integer. I'm not doing any of that stuff, right? This is just junk code to explore this idea of passing a string and then using that string that's been passed to us. And I'm going to need to do some includes. Oh, no, I don't. Okay. So here's my function. If I say something and I say 123, it tells me r equals 123. Hey, that's great. And of course, if I do something weird, right, who knows what r is going to be equal to. And if I do, you know, 4, 5, 6 with some extra stuff after it, it's just going to say 4, 5, 6. So you got to do more to make this, you know, accessible for 10 out of 10. But this is the basic way that you pass strings, right? You declare your function prototype to say it's going to take a char star. And when you write the function, you say it takes a char star, name that whatever you want, and bingo, inside this function, this is an array of characters suitable for passing to scanf, or printing, or doing string length, or anything else that we would do with a string. And when I do my call to parse, I just put in the name of an array, but right, I've got to declare how big that array is before I can say, hey, fgets, put 120 characters into that array. And if I try to do something like this, right, just say char star temp, right, I'm going to seg fault. Because this doesn't allocate any memory, right? I'm telling fgets, hey, you can store 120 characters here. Well, why do I think I can store 120 characters there if I just say char star temp? right? So what I need to do is I need to say, hey, temp has space for 120 characters. And now fgets will take whatever I input and store it there. But then when I get down here and I pass that to string, string is referring to the same thing as temp, which is something that holds 120 characters. So that's our basic string passing mechanism. And when we want to pass arrays, it'll work exactly the same. Generally, in your main program, you declare the array and you also say how big it is. You actually request space for it. And then when you pass it, you just pass the name of the array, which is a memory address. And so in your function, you say, hey, my argument is going to be a memory address, a pointer to whatever kinds of things are in your array. Fgets reads from standard in. And that's all it does. It reads from standard in, saves into memory. Scanf reads from standard in, parses it, and loads values into variables based on arguments that you specify and so on and so forth. But it generally does not save the thing that you read from standard in, which means if you want to go back and reinterpret it, you're out of luck, it's gone. So fgets just reads from standard in, saves in memory. scanf takes that value in memory and interprets it. And so the picture is like this. Fgets takes standard in and loads it into memory. And scanf takes memory and parses it. Scanf goes from standard in and parses whatever the input is, and it skips this middle step. So we're always going to do fgets and scanf. So the 120 here is the size of my array. So I'm telling it don't store anything more than 120 characters. If I decided that I wanted my array to be 10 characters long, I would have to tell fgets, hey, you only have space for 10 characters. All right, other questions about this?
Again, result just is a way to determine if scanf got the right amount of input, and then we can make tests on that accordingly.
Exactly, yeah. And remember, for the ODP, we want to probably scan with a %d and then a %s. And save the first thing with whatever variable you want, but then save the extra thing in just an extra buffer. And then if result is equal to 1, that's good. If it's not equal to 1, then there's a problem with the input. Either there wasn't enough stuff, or there was too much stuff, or the stuff that it found wasn't exactly an integer, or something. Something went wrong. But in any of those cases, right, we're going to, I'm on the wrong one. In any of those cases, those are considered illegal input. You should return a -1. So you're only going to return a 1, 2, or a 3 if your input is exactly a 1, a 2, or a 3. Now don't check to see if it's equal to quote 1. Don't check to see if the first character is the character 1 or something like that. Use scanf. Okay? If your string contains a bunch of spaces followed by a 1, that's considered the integer 1. It should return a 1. So use scanf. Right? But if you scan with this little trick of picking up some extra stuff after the %d, that will pick up all the illegal cases like 2x or 2.3 or things like that. All right. So if the string is empty, scanf will pick that up. If it starts with something that's not a space and not a digit, it'll pick that up. If it's a valid integer, you have to check to make sure it's between 1 and 3. And if it is, return that. If it's out of range, return a -1. And so same as yesterday, you're going to want to write your own test function for this. And your test function can be, you know, just calling your parse function with a bunch of different values. So we could also do something like this. Right? I can define a string by just putting it inside quotation marks. And if I do this, it should pass an array of characters containing 555. And it'll tell me the result is 555. So you can do your test code however you want. You can use fgets to read from the user. You could do that in a loop to keep reading fgets. You could use a command line argument. You can hardwire something like this. But whatever you do, you want to basically test lots of different possibilities for your input. And the ODP runs, I think, 30 or 40 different tests on your parse function. And you got to pass them all to get the 10 out of 10. So test this thing thoroughly, right? You can hardwire, you can input values while your program runs, etc. And you know, build your test bed like this if your test bed is main.c. And then when you think you've got it working perfectly and you're ready to assess, go ahead, build your executable like that, and then assess with this command. And this one I left open till 10 tomorrow, so you can come to office hours in the morning if you're stuck, but don't make that your first attempt, because I'm getting like 10 people in hours in the morning, and I'm not able to get to all of them. So work on this and try to get it to work, and if you're absolutely hopelessly stuck, right, come by office hours, and if you're there early enough, hopefully, you know, I can give you some help. All right, send me an attendance note on the way out, and have a good one. I will see you tomorrow.
Have a good day.
Thanks, you too.
What? Have a good day.
All right, you too.
Have a good day.
Thank you.
Joseph, your